Hello everyone. Welcome back to my YouTube channel, which is Chemical Edda. In this video, we will see another set of questions based on thermodynamics, which is mostly related to the ideal gas law. So, if you like my video, please like, share, comments, and subscribe to my YouTube channel. Now, let's see questions. So, the first question is, state the ideal gas law. The ideal gas law may be stated as, the volume of a given amount of gas is directly proportional to the number of moles of gas, directly proportional to the temperature, and inversely proportional to the pressure. Hence we can write, V is proportional to N into T divided by P, where N is the number of moles of gas, T is the temperature, and P is the pressure. This law also called the universal gas law. Now next question is, what is an ideal gas? So, an ideal gas is a gas which obeys the relation PV is equal to RT, where T is the temperature, P is the pressure, V is the molal volume, and R is the universal gas constant. But, this relation, that is PV is equal to RT, is only an approximation to the actual behavior of gases. Hence, all gases behave like an ideal gas at sufficiently low pressure, in the limit P tends to 0. Now, state ideal gas equation. So, according to the ideal gas law, V is proportional to N into T divided by P. We can write this equation as V is equal to R into NT divided by P. Hence we get PV is equal to nRT. This equation is called the ideal gas equation, or gas equation, where R is the proportionality constant. It is also called as gas constant, or universal gas constant. And the value of R is equal to 8.314 joules per mole Kelvin. Now, what is a gas constant or universal gas constant? So, a gas constant or universal gas constant is the physical proportionality constant in an ideal gas equation. It is denoted by R. According to an ideal gas equation, PV is equal nRT. So, R is equal to PV divided by NT. But, at STP condition, pressure P is equal to 1 atmosphere, temperature T is equal to 273 K, number of moles N is equal to 1 mole, and 1 mole of any gas occupies a volume of 22.4 liters. Hence, R is equal to 1 atmosphere into 22.4 liters divided by 1 mole into 273 K. Hence we get R is equal to 0.0821 atmosphere liters. Mole inverse, Kelvin inverse. Now, what are the values of R in different units? So, from an ideal gas equation, we can write ideal gas constant R as R is equal to PV divided by NT. If the pressure is written as force per unit area, and volume is equal to area into length, then R is equal to force divided by area into length divided by N into T. Hence we get R is equal to force into length divided by NT. As we know, force into length is nothing but work. Hence we can write R is equal to work divided by NT. So, R can be expressed in units of work or energy per degree per mole, while the actual value of R depends on the units of pressure and volume or energy. In this table, we can see values of R in different units. So, if the unit of pressure is the atmosphere and unit of volume is liters, then the value of R is equal to 0.0821 liters atmosphere, Kelvin inverse mole inverse. Similarly, if the unit of pressure is the atmosphere and unit of volume is milliliter, then the value of R is equal to 0.0821 milliliters atmosphere, Kelvin inverse mole inverse. Now, if the unit of pressure is mmHg and unit of volume is liters, then the value of R is equal to 62.3 liters mmHg, Kelvin inverse mole inverse. Now if we consider units of energy as joules, then the value of R is equal to 8.314 joules, Kelvin inverse mole inverse. If we consider the unit of energy as erg, then the value of R is equal to 8.314 into 10 raised to 7 erg, Kelvin inverse mole inverse. If we consider units of energy as calories, then the value of R is equal to 1.987 calories, Kelvin inverse mole inverse. From this table, we can understand that if we know one of the values of R, then we can convert it to another unit if we know the unit conversion. Now, what is the equation of state for gas? So, a mathematical expression of the type function of pressure, volume, temperature is equal to 0, which describe the PVT behavior of substances, is called an equation of state. The ideal gas equation is also called an equation of state for a gas, because it contains all the variables like temperature, pressure, volume, and number of moles, which describes completely the condition or state of any gas sample. Now, state Boyle's law. So, Boyle's law states that the molar volume of a gas, that is V, varies inversely with pressure when the temperature is held constant. Hence we can write V is proportional to 1 divided by P at constant temperature. Hence we get PV is equal to constant. Now, state the Charle's law. So, Charle's law states that the molar volume of a gas is directly proportional to temperature when pressure is held constant. Hence we can write V is proportional to T at constant pressure. Hence we get V divided by P is equal to constant. Now, can we apply the ideal gas equation to all gases at all temperatures and pressure? So, the ideal gas law is only an approximation to the behavior of gases. It is applicable at low pressure and high temperatures, where the density is sufficiently low. It is applicable at low pressure and high temperatures, where the density is sufficiently low. Now, how does an ideal gas differ from real gas? So, the difference between ideal gas and real gas is: in ideal gas, the actual volume of molecules is negligible. And in real gas, the actual volume of molecules is appreciable. There are no attractive forces between molecules in an ideal gas. And in a real gas, the attractive forces between molecules exist. Molecular collisions in an ideal gas are perfectly elastic. And in a real gas, molecular collisions are not perfectly elastic. For the reasons listed above, real gases obey the gas laws under moderate conditions of temperature and pressure. But at very low temperatures and very high pressure, the real gases show considerable deviations from the ideal gas behavior. Now, what is van der Waals' equation of state? So, the van der Waals equation of state is a modification of the ideal gas law, because the PVT behavior of gases differ from that predicted by the ideal gas law. Hence in 1873, the van der Waals proposed an equation of state which takes into account the unavailable volume for molecular motion, that is the excluded volume. While deriving the ideal gas law, it is assumed that the molecules do not occupy any volume. But in real gases, such assumption is not valid, since the molecules do occupy some volume. So, the van der Waals equation of state takes into account the unavailable volume for molecular motion, that is the excluded volume. If we consider gas molecules of spherical shape of radius r, then the center-to-center distance between two molecules at the instant of collision is twice r. Therefore, molecule cannot reach the other molecules, such that its center lies within a distance of twice r from the center of the other molecule. Hence, the center of a molecule is excluded. That is unavailable from a spherical region, which is called the sphere of exclusion, of radius twice r from other molecules. So the total excluded volume, or unavailable volume for molecular motion is B is equal to 16 divided by 3 into n0 into pi into r cube, where n0 is Avogadro's number. Hence, free volume available is equal to V minus B. Now, the second point considered by van der Waals is the attractive forces between the molecules, which leads to a reduction in the pressure exerted by the gas. So, while deriving the ideal gas law, it is assumed that there are no intermolecular forces of attraction between the molecules. But in real gases, such assumption is not valid, since there are forces of attraction and repulsion between any pair of molecules, as in the interior of the gas, the molecules do not experience any net attractive and repulsive forces, because gas is attracted equally in all directions by the surrounding molecules. However, the molecules adjacent to the container wall experience a net attractive forces by the surrounding molecules on one side only. Hence, the observed pressure will be less than the pressure which is exerted by the gas in absence of the attractive forces. Therefore, reduction in pressure, that is P dash minus P, is given by P dash minus P is equal to A dash into N0 by V raised to power 2. Hence the van der Waals equation of state is P plus A by V square into V minus B is equal to RT, where A and B are constant, which is also called as van der Waals constants, and they depend on the nature of the gas. Now, what is compressibility factor? So, the compressibility factor is defined as the ratio of the actual volume to the volume predicted by the ideal gas law at the same temperature and pressure. It is dimensionless ratio. It is denoted by Z. Hence, from definition we can write as Z is equal to actual volume divided by the volume predicted by the ideal gas law. As we know from ideal gas equation, volume predicted by the ideal gas law is equal to RT by P. So we can write Z is equal to V divided by RT by P. Hence, Z is equal to PV divided by RT. For ideal gas, Z equal to 1 at all temperature and pressures. The values of Z shows the extent to which a real gas departs from the ideal behavior. Now, what is isothermal compressibility? So, the isothermal compressibility is defined as the rate of decrease of volume with pressure at constant temperature and per unit volume. It is denoted by kappa. Hence, kappa is equal to minus 1 by V into del V by del P at constant temperature. In this equation, the negative sign is used in order to keep the value of kappa positive, since an increase in pressure will lead to a decrease in volume. Now, what is isentropic compressibility? So, the isentropic compressibility is defined as the rate of decrease of volume with pressure at constant entropy per unit volume. It is denoted by kappa S. Hence kappa S is equal to minus 1 by V into del V by del P at constant entropy. In this equation, the negative sign is used in order to keep the value of kappa S positive, since an increase in pressure will lead to a decrease in volume. Now, what is coefficient of volume expansion? So, the coefficient of volume expansion is defined as the rate of decrease of volume with temperature at constant pressure per unit volume. It is denoted by beta. Hence beta is equal to 1 by V into del V by del T at constant pressure. Now, what is the relation between coefficient of thermal expansion and coefficient of isothermal compressibility for ideal gas? So, the ideal gas equation of state is PV is equal to RT. Hence V is equal to RT by P. The coefficient of thermal expansion is beta is equal to 1 by V into del V by del T at constant pressure. Then after putting the value of V from ideal gas equation and solving it, we get beta is equal to 1 by T. Now, the coefficient of isothermal compressibility is kappa is equal to minus 1 by V into del V by del P at constant temperature. Again, after putting the value of V from ideal gas equation and solving the equation, we get kappa is equal to 1 by P. Now, state the Rudleach-Kwong, that is RK equation of state. So, Rudleach-Kwong, that is RK equation of state, is P is equal to RT divided by V minus P minus A divided by V into V plus P, where A and B are characteristic of gas, and these parameters are related to critical constants, where A is equal to 0.4278 into R square into Tc square divided by Pc, and B is equal to 0.4278 into R into Tc divided by Pc. Now, state the virial equation of state. So, virial equation of state. Express the compressibility factor of a gas or vapor as a power series expansion in terms of pressure or 1 by volume. Hence, the virial equation of state in terms of pressure is Z is equal to PV by RT is equal to 1 plus B dash P plus C dash P square plus D dash P cube. Now, the virial equation of state in terms of volume is Z is equal to PV by RT is equal to 1 plus B divided by V plus C divided by V square plus D divided by V cube, where B dash, C dash, D dash and B, C, D are known as virial coefficients. These coefficients are functions of temperature only. The virial equation finds its greatest application at low to moderate pressures, because it can be derived from kinetic theory. It is on theoretical basis and is free from arbitrary assumptions. Hence, virial equations distinct from other equations of state. The coefficients also can be given physical interpretation, and they account for the molecular interactions, where B and B dash are called second virial coefficients, which take into account deviations from ideal behavior, which results from interactions between two molecules. And C and C dash are called third virial coefficients, which take into account the deviations from ideal behavior that results from the interactions of three molecules. So that's all about important questions based on thermodynamics, which are mostly related to ideal gas equation. In next video we will see another set of questions on thermodynamics. So, if you like my video, please like my video, share this video with your friends, and subscribe to my YouTube channel, which is Chemical Edda.